What's up, scholars? We're starting our Unit 8.1 today on torque and rotational motion. As I've said, and as you can see here, for this unit we're going to take everything linear that we've learned and we're going to spin it. So everything linear is going to become rotational, or sometimes you might hear me say angular. So what that means is all of the equations and intuition that you've built up for linear motion, for linear force, all of that will translate to this new unit. So here's a classic example of something we would have done first semester. We can look at a person pushing a box across the floor, some displacement delta x. You know, often we go shorthand and say distance. Here, let's be very careful and say displacement. It'll start with some initial velocity v naught. It'll end with some final velocity v final. And to get there, it will undergo some acceleration for some time t. Now, the cool thing about this is that everything in this linear example has a rotational or angular equivalent. I want to show you what that picture looks like here. So what I've got here is a fairly okay drawn merry-go-round. Let's put this on like a, there we go, that makes more sense. Alright, so we've got a merry-go-round. This person is exerting a force at some distance r away from the center of the circle. That amounts to a torque. We're going to talk lots more about torque. Torque uses this funny Greek letter tau, T for torque. And let's just say that they started the merry-go-round moving here and it ended over here. We would say that this was the initial angle theta, and this over here would be the final angle theta final. It would have started with some initial angular velocity omega naught, and it would have ended with some final angular velocity omega final. So the overall displacement there, I guess we can label up here, this would have been x naught, x final. We can say that this had a total displacement, angular displacement of theta final minus theta initial, just like we can say delta x equals x final minus x initial. The other variables that we're missing are the acceleration. We tend to use this funny little symbol here, alpha, or fishy, sometimes you might hear it called. And then I think the only variable, one of the only variables that's going to stay the same is t for time. I misspoke, I've left out one more variable. Here we're pushing in a straight line. We've got linear displacement, linear velocity, linear acceleration, just regular old time. We've got linear forces. The thing we've left out is what happens with mass if we try to apply a torque to it. And what we end up with is a new symbol or new letter that we're going to use called I. That is what's called the moment of inertia. Now, I've laid out both of these situations before, and what's really cool about this is that the equations that we used to describe all of this information, they have 100% perfect analogs in this type of rotational situation where we're speeding things up, we're slowing them down, but now we're doing it in a rotational sort of way. So the next thing I want to do is show you the old equations that we had and link them up with the new equations. So I've got what hopefully looks like some fairly familiar equations. We've got the displacement equation, the final velocity equation. Oops, that should just be an AT. Sorry about that. Fixed. And we've got the v squared equation, one of our favorites, where we actually just simply combine those first two. And then we also have sort of our bread and butter, means second law. It turns out that each of these has an analog. Now I recognize that I have not yet defined each of these terms, but take a moment, see if you can figure out what's what, and see if you can correctly write these equations out. Now do it in pencil, just in case you make any mistakes, but I'm going to do that now. So there you've got it. Instead of linear displacement, we've got angular displacement. Instead of initial velocity times time, we have initial angular velocity times time. Instead of 1/2 at squared, we have 1/2 angular acceleration times t squared. Same here. The angular velocities are replaced and the angular acceleration is replaced. the angular speeds, the linear speeds squared replaced by the angular speeds squared plus 2 alpha times the angular displacement. And then finally, we have got Newton's second law, but written for torques. Here again, you can see that funny I letter is for the moment of inertia. So here I've got those written out in words. We've got initial and final position. We've got displacement, which is just the difference between the two. Initial and final velocity. We've got linear acceleration. I should write that. Linear accel. We've got mass, and we've got force with their appropriate units. Let's go ahead and define the angular or rotational quantities. So we can make direct comparisons here now that I've gotten it written out. For x naught, that was the initial position. And here we've got the initial angle or the initial angular position. So I've just inserted the word angular, and that's kind of it. That's the direct way to translate it in words between the two. Instead of final position, I have final angle or final angular position. I just went with, for delta theta, that's just final angle minus the initial angle. That is the angular displacement. How far around a circle have we gone? Continuing with the somewhat, hopefully, obvious trend, we go initial velocity to initial angular velocity. Instead of, here's where it gets a little bit tricky, instead of meters per second, the thing that we measure distance for angle or displacement for angle is in degrees or usually radians. So what that means is that the angular velocity, no matter which way you're going to do it, is going to be radians per second, because that's how we measure how far around a circle that we've gone. You can also do it in degrees or revolutions, but that's the base SI unit. Let's continue. So we've got next our little alpha or fishy symbol. That's the angular acceleration instead of just the regular linear acceleration. And instead of meters per second, it's in radians per, instead of meters per second squared, it's radians per second squared. We've got just two more. All right, our remaining two, we're comparing the linear mass, something's resistance to being pushed in a straight line, versus something's moment of inertia. How hard is it to rotate that thing? So the analogs there are very, very similar. We're going to talk a lot more about moments of inertia coming up. And then we've got force. Its rotational equivalent is often called torque, with this sort of funny looking umbrella. That is the Greek letter tau. So there are a couple ways we can define torque. We'll get a lot more into this. You can do force cross product with r, or force times the distance you're pushing away from the fulcrum. We'll look a lot more at that. Or you can do, as I showed before, the sum of the torque on something is equal to the moment of inertia times the angular acceleration. This is Newton's second law, but for rotation. The units here are a little funny. There's no agreed upon name. It's just newtons times meters. That is the measure for torque, or the unit for torque, rather. All right, let's do a quick example. So let's say we've got a wheel with some unknown torque being exerted on it. It has a moment of inertia of 10 kilograms meters squared. It has an initial angular velocity of 0 radians per second, otherwise known as standing still. By the end, after 5 seconds, it is now going 250 radians per second. So the ultimate thing we want to know is how far did the wheel go? That would be in terms of angle, so delta theta. We also would love to know, actually, in order to answer that, what is the angular acceleration and what is the net torque. We'll put net torque on our object. So let's dig into part A. We're going to use the second angular kinematics equation. So omega final equals omega initial plus alpha t, where these are the initial speeds, which we know. We already know the time. So let's do some rearranging and solve. So you can see I've done some rearranging. This is the angular acceleration is equal to the change in the angular velocities, just like acceleration is equal to the change in regular velocity, divided by time, of course. So that would be 250 minus 0 radians per second all over 5 seconds, and we end up with an angular acceleration of 50 radians per second squared. So you might wonder, is that fast? Is that slow? Keep in mind that one circle is 2 pi, or about 6.28 radians. So if we take 250 and we divide by, let's call it, 2 pi, you get about 40 rotations per second here. That's pretty fast, and this is increasing that speed very rapidly as well. So this is quite an acceleration. This might be something weird like an angle grinder or something of that nature. Now let's look at the torque. If you look back at some of our comparisons, the net force, F equals ma, very similar to the net torque. It's equal to the moment of inertia times the angular acceleration. So F equals ma, T equals I alpha. So T equals I alpha. We want to know the net torque. We now know the angular acceleration and the moment of inertia. So that is a pretty straightforward calculation. 10 kilograms meters squared times 50 radians per second squared. And we will end up with, what is that? 500 newtons times meters. Trust me, that does really end up working out. You've got kilograms meters per second squared, that's a newton, and then you've got an extra meter hanging around. We'll talk more about units as we move forward. Now the last thing we might want to know is how far did, for example, this part of it move. I've got a little dash there. And this is actually very similar to how an odometer works on a car. So let's try that as an example. So there are two ways we could solve this. Perhaps the most straightforward way is to recognize that the initial angular velocity is 0 and plug into this equation. The other way is by starting with the omega final squared equation and solving it for delta theta. We know everything else. I'll show the algebra now. So we've got canceling out the omega naught because it was 0. We plug everything in and we end up with, so when we plug all that in, making sure we square, you'll notice that the second squareds cancel and end up with 625 radians. We'll do our little trick and divide by doing it with parentheses so I don't mess it up. 2 pi. It's, like I said, 2 pi is about 6.28, so this is almost exactly 100 times that this thing goes around in just those 5 seconds. Just for completeness, I've solved and plugged it in over here. We also get 625 radians. So what I'm hoping you gathered from this is several things. First, everything you learned about linear situations has an exact rotational or angular analog. In fact, all of the equations translate directly. We were able to write down all of the definitions of those symbols and their units in both types. And then we did a quick example showing you that it's really just an application of the same types of equations that we did before. And that's all there is for now. Thanks so much, folks. Bye.